Okay, welcome to the lecture of theory of thin film growth. As you know, we discusses in our previous lectures also on the topic of theory of thin film growth. Today, we have planned to focus on the topic of the growth transformation, or we can say that the nucleation transformation. Okay, so let us imagine we have a volume of material. We have some kind of volume of material. Suppose let us observe that this is our volume of our particular material, and which is going to transform. Okay, so inside that there is some kind of material. If we consider this is the our volume of our particular material which is going to transform. So let us consider the given box is represent the transform material and gradually is going to transform. Okay, so this is our volume of our material, and now we are going to focus on the topic of transformation. And let us consider that inside this box is represent the transform material and gradually is going to transform, so that the transformation will begin with some nucleation, and that nucleation event we are going to focus on the current topic. Okay, so that inside that particular volume of that material there are some kind of nucleation or some kind of nucleus was present. So we can say that this is our nucleus, which are primarily available, or we can say that they are primarily we are deposited by using some kind of system. So that red spot indicates the nucleation events. Okay, if suppose there are 4 nucleus was available. Okay, so that if suppose that 4 nucleus was available, now some nuclei of critical size. Okay, these are the some of the nuclei having some of the critical size have formed in a given some time interval. Okay, now what will happen? These are the primary nuclei which is available, and after this some time of interval, what will happen? Some nuclei of critical size have formed in a given some time interval. As the time passes, so what will happen? That nuclei was growth. Then that nuclei was growth slowly in this way. Okay, so we can say that the nuclei was growth. That red circle indicates after some time interval that nuclei was expand. We can say that that nuclei was expand slowly. Okay, that nuclei was formed. Okay, now what we'll observe here, as the time passes, whenever some kind of nuclei was formed as given some time interval, and as the time passes, these nuclei have growth. Okay, and at the same time another small nuclei was created. So that nuclei was expand or growth in this direction. Okay, so this nuclei was formed or growth in this direction. So simultaneously what will happen? Another few more nuclei was formed at the same time. Okay, simultaneously there are a few more nuclei was formed. Okay, so these are the nuclei. Let us assume that these are the nuclei. Now let us assume that again after some time interval, or we can say that as well as the nucleation is even will happen. Okay, so simultaneously this nucleation is happening here, means inside that nucleus, for better understanding purposes, if suppose this nucleus was growth in that circular ring way, okay, and at the simultaneously or at the same time some of the nucleation was formed here. Okay, so now we can say that again after some time interval, in the next time interval, already nucleation region keep growing. Okay, so now after some time interval, whatever the first nucleation was formed, so it keep growing, which I have represent in different colors. Okay, in this way, that primary nucleation nucleus, or we can say that primary nucleation region is continuously keep growing and further new nuclei get added. Okay, further some nuclei get added. Okay, that primary nuclei, the secondary nucleation was keep growing in this way. And what will happen at simultaneously, what will happen, the new nuclei get added to that particular system. Okay, to that particular system. Okay, so suppose few more nuclei was added again, we are added here, again we can added one more nucleus here, again the nucleus was added here. Okay, now what will happen, again after some time interval, or we can say that again next event called the existing particle which are growing and will keep growing and still new nuclei can form. Okay, so simultaneously again after some time interval, that primary nuclei was keep growing. Look it here, this is the primary nuclei which is keep growing. Okay, these are the primary nuclei. Okay, and after that secondary portion, okay, that secondary nuclei was formed, that also simultaneously growing. And currently these nuclei are also growing, or growing means we can say that it's expanding, it's expanding. Okay, and up to when that nuclei was growing, if that still new nuclei can form. Okay, again here the new nuclei can form again after some expandation or after some growing, again there are some nuclei was formed here, we can say that here. Okay, now so one can see that the gradually in this process of nucleation in growth, okay, new nuclei are forming and already existing nuclei are growing. Okay, so I repeat again, so one can see that inside the figure, the gradually in this process of nucleation in growth, new nuclei are continuously formed. Okay, and already those who are existing, some of the nuclei are already available, such as this one, such as this one. Okay, these are continuously growing. Okay, so what will happen, overall transformation rate will depends upon the nucleation rate and the growth rate. Okay, so this overall transformation is depends upon the nucleation rate and growth rate. Okay, so again what will happen? Again in the next stage, here again the nucleation was growing. Okay, and I will show that in red color, sorry, green color. Again that nucleation was growing. Okay, but if after some time, after the growing of some time, there some of the nucleation growing was impinging. It means they are merged. Okay, somewhere they are merged. Look at here in this part, they are impinging in the different another nucleation point or another nucleus. They are impinging or they are impinged in between the another portion of that point. Okay, after some time interval. Okay, so if suppose all the nucleus was growing, and after some time some of the nucleus was what? They are impinged. Okay, in this way. And how they are impinged? We can observe here, that point we can observe here. Okay, in this zone. Okay, in this zone. Look at here, in this zone. It means the two nucleus are impinged in each other. Okay, or again simultaneously what will happen? Again some nucleation was formed. Okay, suppose here is some nucleation was formed, here some nucleation was formed, and again that in existing nucleus was again expanding or growing or keep growing. Okay, or which I have showing in a pink color. Look at here. And now in this step we can easily obtain that after the growing they are completely impinged towards the another nucleus. Getting my point? Here also look at here carefully. If we draw the spherical or complete circular growth, because that growth was possible in all the direction. Okay, and due to that reason that particle was, or we can say that the nucleus was impinged in other nucleus, okay, and here you can say that it's completely impinged towards each other, and after that we can observe that the nucleation growth was saturated, or we can say that the nucleation growth was stopped. Okay, means the nucleation growth was the steady state in this way. Okay, fine. So what we observed here, or what we obtained from this figure, we can say that after some time of growing, the nucleation was impinged. Okay, and due to that reason, the particles, or we can say that the nucleus growth was stopped. Okay, so how we can calculate the nucleation rate? Okay, these are the rate of the nucleation, because and how we can calculate the growth rate? Okay, nucleation rate means what? At what rate new particle is forming? Okay, whenever that particles are still growing means what? In this direction, I would like to indicate in dark color. They are growing continuously in this direction. Okay, so whenever the particles, or we can say that the nucleus are growing, and whenever the new particle is forming, that particle rate is nothing but a nucleation rate. Okay, nucleation rate is nothing but at what rate new particle is forming. Okay, so that nucleation rate was indicates in terms of capital I, in terms of capital I. Okay, and the unit of that nucleation rate, which is denoted by per meter cube, per meter cube per second, per second. Okay, so this is the unit of nucleation rate. Okay, so if we define the nucleation rate, so the definition of nucleation rate is indicates in terms of, or we can say that the number of nucleation events. I will write here number of nucleation event per unit volume per second. This is the definition of what? This is the definition of the nucleation rate. Nucleation rate is, okay, so this is the definition of nucleation rate. Okay, and how this growth was formed? We can see that this black arrow, we can see that this black arrow inside the figure. Okay, this is the growth rate. Okay, this is the growth rate. Okay, and how the growth rate was formed, and what is the definition of growth rate? Okay, so growth rate is means at what rate this interface is growing, that will be a growth rate. Okay, so what is growth rate? I am writing here what is growth rate. Growth rate is at what rate this interface is growing, that will be a growth rate. Okay, so in simple way or simple definition is that the growth rate is at what rate this interface is growing. Okay, so which interface? I am talking about this. I am talking about this. Okay, I am talking about this. This is the growth rate, and which is denoted by, how we can calculate that growth rate, which is denoted by G, capital G. Okay, and which is represented in terms of small d, capital R by dt, if we differentiate that term. Okay, and the unit is meter per second. Okay, so the rate of increase of the size of the particle, that is the growth rate. That is the growth rate. Okay, so overall transformation rate we can determine by using the dx by dt. If we differentiate the rate, okay, that is the fraction transform per second. Okay, so now next point or next point, our aim is that how overall transformation was formed. Overall transformation rate is dx by dt in per second inverse. Okay, so how we can judge and observe that overall transformation? So in terms of by using the fraction transform per second, so which is represent in terms of capital X, that is the fraction transform, capital X. which is equal to the fraction transform, fraction transform. Okay, and that growth rate which we can imagine or calculate by using the graph also, or by using the graph we can observe that growth rate also. So how we can observe that? So I will show you by using the graph. If this is the x-axis, sorry, this is the y-axis and this is your x-axis. Suppose this is your x-axis, okay, and x-axis indicates a growth rate time. Okay, x-axis indicates a growth rate time, and y-axis indicates a what? X. That is the fraction of transform. Fraction transform x. Okay, so here somewhere the ratio, this point indicates a percentage. Okay, so here we have considered the 1. Okay, it means the 100% growth transformation was completed. Okay, and here is the origin 0. It means the initial stage. We can say that this is the initial stage. Okay, it means from here the nucleation was added, and after this some point the growth transformation was formed. So here how the nucleation we can draw plot here the dashed line is in this way. Okay, and now how the growth transformation was happening. So we can say that this type of growth transformation we can observe. This is the stable. This is the stable zone. Stable zone means it completely growth transformation was completely over. Means the two nucleus are impinged with each other. If suppose here in this area, if you allow further growth, the particles will start impinging, and the region where they impinge and further growth is not possible. Here, look at here in first figure. Observe, look here. Okay, look inside this figure. Okay, so here the nucleation was impinged. Here the nucleation was impinged, and due to that reason, the further growth is not possible here. Okay, and due to that reason, it observed a completely steady state. Okay, and if we found here, if we observed here, if we look inside here, so here less number of nuclei was formed, and if we look here in this zone, the slow down due to the impingement. Here the impingement was formed. Okay, it means the nucleation or two nucleus are impinged with each other. It means they are merged slightly, and due to that reason, due to the slowdown impingement was found here. Okay, so that we can observe that the number of particles which are growing will increase as a function of time. So overall transformation has found. Okay, so from this spectra what we observed, number of particles which are growing will increase as a function of time. So overall transformation was found. Okay, so this is all about the growth transformation. This is all about the growth transformation. Wherever the impingement takes place, the transformation will end. Okay, so last sentence I would like to say that wherever, I will write here for better understanding purposes, wherever the impingement takes place, the transformation will end. Transformation will end. Shown in graph as well as figure. Shown in graph as well as figure. I will write wherever the, okay, so that last sentence indicates that wherever the impingement takes place, the transformation will end, shown in the graph. Okay, so both the figure, you can observe that in both the figure 1 and graph. Okay, whenever the nucleus was merged together or impingement was happen, or in at that time you can see in this area. Okay, it means, and this area indicates the transformation will end or transformation was over. Okay, so this is all about the nucleation transformation, or we can say that the growth transformation.